In this lecture, I'm going to cover chapter 14 of the textbook, which introduces the idea of cross-validation. So my presentation is slightly different from that in the textbook, so just be warned that I spend more time unpacking the practical details of computing the cross-validation statistics than in the textbook. So my lecture is kind of a complement to what's in the book. So, but make sure that you read chapter 14 as well. So the first thing I want to talk about is k-fold cross-validation, because that is the central idea that I want to communicate here. And in practice, most of the work that we do involves k-fold cross-validation. So it's good to understand how this works from the very outset. So the way this works is as follows. What we're going to do is, once you have the data, you're going to split the data into k sets, and it works like this. So let's say k is 10. So you're going to split the data 10 times in the following way. 90% of the data will be called a held out set. Oh, sorry, 10% of the data will be called the held out set, and 90% of the data will be the training data, right? So if we have 10 k equal to 10, we're going to do this 10 times. So we will iterate 10 times. The first time round, we'll take the full data set, and then we're gonna split it pseudo-randomly such that 10% of the data is the held out data. Call it, it would be a vector, and it's the kth fold, right? So the first time that we do this k will be equal to 1, and we have a vector of held out data. Then what we'll do is that we will train the model on the non-held out data, so on the training data. So what we're going to compute is the posterior distributions of the parameters using the training data. So that's represented with y minus k, which represents that this is not being held out. This is the data that's being used for training. So what the upshot of all this is that what you get in the end is posterior distribution on the parameters in your model that are trained on, that have been computed based on the training data. The held out data did not play any role in all this. Okay, so once we have those posteriors, and we're going to use those posteriors to compute the log likelihood of the held out data. So that vector y sub k, right, that's the held out data. We're going to compute the log likelihood of the held out data given the posteriors that we've already derived from the training data. So what we'll end up with is the log likelihood of our held out data given the training data. And so what we are doing here is that we are integrating out or marginalizing over the theta parameters. So I will show you later how this is done. It's just summing over all the samples that we have eventually. Okay, that's what will happen. Okay, so once we have the log likelihoods of all the data, right? And why log likelihood? The reason is that the logic is that the higher the log likelihood of the held out data, given the posteriors that we have and the model that we have, the better the predictive fit of that model. That's the logic, okay? So the higher the log likelihood, the better the quality of the fit. So what we're going to do is, if we have S simulated values for each of the parameters, and we are going to do k-fold cross-validation, so k is some particular value, this small k, some particular value between 1 and 10, we're going to compute the log predictive density for each data point in that particular fold in the following way. Right? We're going to take the likelihood, okay, so not the log likelihood, the likelihood and of the held out data in the kth fold, and we are going to sum up the likelihoods for all the samples that we have for theta. So let's say you have 4,000 samples. So you're going to do this 4,000 times, this summation, right? For every single data point, we're going to do that, right? And so for a given, this is a single data point I'm talking about in the held out data vector, okay? So for that single data point, we take all the samples we have from the posteriors and compute the likelihood for that data point for all those values, sum them up, and then take the divide by the number of samples. So basically we are taking the expectation, right? So that's what gives us for a held out data point I, it gives us the expected log pointwise density. And of course it's an estimate, that's why we call it a hat ELPD. Okay. All right. So this gives you what's called the pointwise ELPD hat, because this is the ELPD hat for one particular held out data point. So if you have n held out data points, then you're gonna if you have n held out data points, you're gonna get n ELPD hats for each of those data points, and that's called a pointwise ELPD hat. Later on, we'll see how to visualize all this. Okay, how to visualize the pointwise ELPD hats, and that will help us understand which model is doing better and why and where. Okay, for which data points. So all that is coming later. So now we've got the ELPD hats for each one of those data points, held out data points. So we sum those up, and that gives us the overall ELPD, right? Expected log pointwise density. So that's going to be our metric for the quality of fit, okay? And the standard error will be calculated like this. We will take the variance of uh, the pointwise densities, the vector of pointwise densities. Let's say it's called y. We'll compute the variance of those those values and multiply by the number of held out data points that we have and take the square root of that. Right. So the derivation for this just relies on random variable theory, and this gives us a standard error of the ELPD estimate, this one here, right? So we get something like a mean here and something like a standard error here, okay? So then you can do your inference based on that. So the notation in the textbook is a bit different, but the algorithm is the same, right? You will see later on when I unpack the algorithm with actual stand code and the aftermath of the stand code, you will see how these equations pan out, you know, how what they give us, okay? So this gives us the upshot of all this is that for any given model, we can compute the ELPD hat and its standard error, and then we can compare those two ELPD hats to figure out which model is better. So in the next part of this lecture, I'm going to talk about a practical application of this approach. We look at the N400 effect using variation on cross-validation, which is called PSIS-LOO. So that's coming up next. So we're going to start our study of cross-validation with a very simple application using built-in front-end functionality in brms. And so what we're going to do, and LOO, the LOO package. So what we're going to do is we're going to look at the N400 effect that we've seen earlier, that was studied with the base factors, in the chapter before this one. So the predictor here is the close probabilities centered, of course, right? So just like before, we're centering the close, and what we want to know is if there's an impact of the centered close on the N400 signal. Okay, so we fit the full model, which is a hierarchical model, standard hierarchical model with the usual, priors, fixed effect intercept, fixed effect slope, intercept and slopes by subject, intercept and slopes by items. We've seen that before. Here are the prior specifications. And so here, unlike base factors, one thing to remember is that in cross-validation, The priors only matter to the extent that they bias the posterior. If the posterior is biased by the prior, either because it's too informative or it's not informative enough, then you will, of course, get different values for your cross-validation statistics, but they are not as critical. The priors are not as critical as in the Bayes factors. All right, so we can set up the null model by just removing the slope, fixed effect slope from the full model, and we update the model to get the null model here. So now we have the null model as well as the full model here, right? So we want to compare these two models. And there's a function that we can use from the loop package, which computes an approximation of leave one out cross validation. So leave one out cross validation is the extreme case of k-fold cross validation, where you leave out exactly one data point each time. Of course, computationally very expensive. So this front end, loop function in the loop package gives you an approximation of that leave one out cross validation pretty easily. Given the full model, it will return something called ELPD-LOO and some other statistics which I won't talk about because we won't use them. So we are getting some ELPD-LOO value with a standard error, just like I discussed earlier, right? So this is the expected log pointwise density and its standard error, as I explained earlier. Here you have to be careful that in this approximation, something called the Pareto K estimates need to be below 0.7. And we'll see an example about when they're not later on and what to do about this. Okay, so it's just a kind of diagnostic tool that they've put in. The details are not really important. We do the same thing for the null. They're not important. The details are not important because we'll be using k-fold cross-validation. Okay, so and we won't be using this shortcut method, which is efficient but an approximation. So we compute the LOO for the ELPD-LOO for the null model as well. And then we want to compare this estimate along with the standard error with this estimate here, right? So what's the difference between the full model's ELPD-LOO and the null model's ELPD-LOO? So higher values are better, right? So when you now compute the difference between the two, you can compute the difference by using the LOO underscore compare function in the LOO package, which takes the full model, null model, and compares the difference between the two ELPDs, ELPD-LOOs. And so the null model has a slightly lower ELPD, but the standard error of that difference, and I will show you later how to compute that, is so broad that we can't really conclude anything. So we have no evidence either way whether this model or the full model is better than the null model or not. One interesting thing to think about is that, you know, those pointwise ELPDs that I mentioned in the beginning of the lecture, they can be extracted from the, the ELPD-LOOs that we computed, remember, here, right, in the full model, I saved the result of the LOO function here that was taking as input the full model, and in this object are the pointwise ELPD estimates, right? So you can plot those against the null model's pointwise ELPDFs. So here are the pointwise values that I'm extracting from the full model versus the null model, and you can look at the difference between the two, right, in a plot that looks at the effect of the different values of close that you have in the data set, and then on the y-axis you're seeing the difference in the ELPD values. Any value that is above 0 is favoring, well, how's the subtraction done here? Yeah, the subtraction is done by subtracting from the full model the null model. So what that means is that when these values are larger than 0, that favors the full model. When they're lower than 0, they favor the null model. And what you can see is that all the values are roughly distributed evenly between the positive and negative values. That's how we end up with an inconclusive effect of close on the on the N400 signal. Okay, so that's an example of using PSIS-LOO with the BRMS functions. That's a quick and dirty way, so to speak, of computing some approximation of leave one out cross-validation, which is a special case of k-fold cross-validation. So next we are going to look at cross-validation with using k-folds instead of leave one out cross-validation or an approximation thereof. The next thing we'll look at is cross-validation, of course using BRMS for now, with the k-fold approach as opposed to the PSIS-LOO method that we just saw. One advantage of the k-fold approach, k-fold cross-validation, is that it removes one layer of approximation that happens in the PSIS-LOO CV, because the PSIS-LOO method is approximating leave one out cross-validation. And so there's no concept of a Pareto K value that you have to worry about like in the PSIS-LOO case, right? So one problem, of course, with the k-fold approach is that the training set will be somewhat smaller because it's not simulating or emulating leave one out cross-validation, but we take 90% of the data for training, and so that we end up with less data, leading to more uncertain posteriors on the parameters, which in turn leads to worse approximation to the true generative process, right? Which of course is unknown. So one of the issues in repeated measures data is going to be that when you create your training set, when you subset the data such that you have 90% of the data, you need to make sure that the subsetting is stratified. What that means is that you want to make sure that you retain some proportion of each subject's data in your training set and only remove a proportion of each subject's data for the testing stage, right? For the held out stage. It shouldn't happen that you randomly remove all the data from one particular subject, and so there's no data coming in from that particular subject in the training stage. That will definitely create a worse fit on the held out data because of large between subject variability, right? So if you've got a subject that was never shown to the model, then you're obviously going to get pretty bad fits to that subject in the held out stage, right? So in order to deal with stratification in the BRMS package, there's a function called kfold where you can set a setting called stratified, and you can specify which group you want to stratify over. And you will also see in the code below the use of the future package. This is just used to parallelize the model fitting, and you can look up the details of this, but it just makes things faster. So my code, which I'm showing you now, will take some time on your computers, like especially if you're using Windows computers, it's going to take forever. So be careful about when you start the process. On my machine, uh, which is a MacBook Pro 18.2 with an Apple One M1 Max, with the operating system Tahoe, I don't know how to pronounce that, with a memory of 64 gigabytes and 10 cores, with 8 performance cores and 2 efficiency cores. It took about 30 minutes, okay? But it will definitely take longer if you have a less powerful machine. So anyway, so like what we are doing here is that we are running the fitted models which we had already fit for our PSIS-LOO. We are going to just run them through the k-fold function in BRMS, defining your folds to be stratified and defining the subject as the grouping factor. And we are just using one chain here because we know that these models converge So we don't need to check the R hats or anything, or we don't need to check for, fat hairy caterpillars or whatever, right? We know that the models converge. So that's why we're just speeding up the whole thing. So, oh, actually, I'm wrong about this. So this 30 minutes that it took happened when I ran 4 chains. Okay, these were 4 chains, and that's why it took 30 minutes. With one chain, it's going to be much faster. Okay, so you can scratch this comment from me. But the fact remains that, like on less powerful machines, you're going to have to spend some more time because the model will be refit, with 10 folds. So each model is being refit 10 times. And so if you have two models, you've got 20 models that you're fitting here. And this is a tiny data set we are working with. If you're working with a serious data set, you could be there for days. So just be warned, and don't try to do this at the last minute or anything. Okay, so k-fold cross validation, as I said, will take time, but you can get the result would be running it through k-fold. The k-fold function will give you the ELPDs and all that. So you can look at the ELPD value and the standard error of the ELPD for the full and the null model, and then just use LOO compare just like always for comparing the two models, like expected log pointwise density. And here we can see that we don't have any evidence for any important difference between the two models, right? So one thing to remember is with k-fold, because we are pseudo randomly holding out some subsets of the data, each time you run the k-fold cross validation procedure, there'll be slight differences in the results because you'll be holding out different uh, data points, right? So there can be some variation. So a good idea is to run the k-fold function a couple of times to see that the expected log pointwise density is more or less, stable. So then the next topic that I will cover is leave one group out cross validation. There we will actually leave one or some subjects out entirely to make to check whether the the model performs well on an unseen subject. So that's a different question that's being asked. The question we were asking with k-fold was, having seen a subset of the data, can the model predict the held out data stratified, of course, right? Having trained on a stratified data set. Okay, having trained on a stratified fold when you're training the model. So that's the whole story about k-fold cross validation using BRMS. Of course, one advantage of BRMS is that it's all very quick and easy. Like you just have to fit your canned models and write your canned models in BRMS, and it just takes a couple of commands to do this k-fold cross validation. That's the upside. The downside is that we have no idea what's actually happening behind the scenes, right? And if we had a customized stand model, which is coming up in the next chapters, right? We'll have multinomial processing trees, we'll have mixture models, and a ballistic linear accumulator. So all kinds of stuff is coming up. There you have models that don't have any shortcuts in BRMS. So you can't define them in any other way except by using stan. And so in that situation, you would have to do some more coding, and that's coming up later. Okay. So there are some advantages to using, these built-in functions in BRMS for doing k-fold cross-validation, but they will not scale for customized problem solving, customized model comparison, which is usually the norm in when you're doing process models, computational models of cognitive processes. Now the next topic is leave one group out cross-validation. So it's in abbreviated form, we generally say logos CV. So what this does is that let's say you have 37 subjects. Now you're not going to have 10 folds, but you're going to have 37 folds. And in each fold, the held out data will be from one of the 37 subjects. So the model will be fit 37 times, okay? So here, of course, as I mentioned, the question being asked is different. The question being asked is whether we can generalize beyond the subjects that we have seen. All right, so again, we use the future package to speed up stuff. And now we are not, when we use the k-fold function, we don't need to say stratify because we are going to just leave a group out. So that's what the function does if you don't specify the stratification, parameter. And so as I said, this will take a long time, but the end result is still the same, right? The two models are not distinguishable. They can't, one doesn't do a better job than the other in predicting the data of the unseen subjects. Okay, so that's in this case at least there's no difference in the conclusions, but the questions being answered are different between logo, CV, and um, k-fold cross validation, as we discussed earlier. Another interesting application of cross validation is when you want to compare the predictive fit of different likelihoods. So the classic problem that we discussed in chapter 3, where we showed that the Gaussian likelihood is a much worse likelihood to use for reading times because reading times are positive only, and a log normal is generally a better likelihood function to use. So we can investigate this with cross validation as well. The important thing here is that if you're comparing different likelihoods, the dependent variable has to be the same, right? So luckily for us in this particular problem, we can do that because the dependent variable will always be reading time, both in the log normal and the Gaussian. Okay, so this is the Stroop data where you have congruent versus incongruent um, words on the screen. The congruent words are those which have written in the color green and uh, spell out the word green. The incongruent words are those in which the word and the color don't match. So you could have yellow written in green, you know. So that takes longer to process because of the mismatch in the cues. You're getting two conflicting pieces of information. One is the color information, the other is the word that you're automatically processing as well. So it's hard to put those two things together to be able to respond as to what color it is. Okay, that's the Stroop effect. And so here we're fitting a model with the log normal likelihood. Just be careful, like this happens every year. People forget that when you're working with the log normal likelihood, the priors have to be on the log scale. You cannot have priors, for example, for the intercept being 500 mean and standard deviation, I don't know, 50 or something. That would be an insanely broad prior going from minus infinity to plus infinity, okay, for on the log scale. So please be careful when it's a log normal, we are working with priors on the log scale. Okay, so that's the full model with the log normal likelihood. Here we've also fit the null model. Actually, I don't know what this is. I think that by accident I've got like two instances of the same model here. Yeah, there are two instances of the same model here. So just ignore this. I will just fix this in the code so that you see only one. And then we can calculate using LOO. Once we fit the model in BRMS, use LOO to get the ELPDs, you know. So here are the ELPDs for PSIS-LOO, and you will also get these Pareto K estimates. Everything looks good here. So for the full model, sorry, not for the full model, for the log normal model, everything looks good. Okay. Now let's fit the same data on with a Gaussian likelihood. So here things go south, right? For one reason, and the reason is that the Pareto K values, there are three of them that will be too high, larger than 0.7. Notice here that because of the Gaussian likelihood, I'm sorry I'm belaboring this point, but I get so many people making the same mistake over and over again that I have to say it multiple times, that if you have a Gaussian likelihood, you're working on the millisecond scale. So your priors have to reflect that. Now I can't use a 6, like I can't use the log normal prior, normal 6 and a standard deviation 1.5 for the intercept. That would be equally insane because that says that the average reading time is 6 milliseconds with a very small standard deviation, which doesn't make any sense, and your posterior will be completely influenced by the prior then because it's so tight and it's so small. Your posterior will always, for the intercept, for the grand mean reading time, will always be near zero, you know. So that's a useless, that would be a useless model. So don't forget to change the priors. Anyway, so we fit the prior, same dependent measure, but different likelihood. Okay. So once we do that, you can, well, first of all, you have to deal with the problem that you've got these Pareto K values that are too high. So if you print out the, the output of the loop function, it will print out a bunch of warnings. It tells you that there are three diagnostic values that range from bad to very bad, So, so basically all you need to do in BRMS, I mean, not in BRMS, in LOO, is to just add another parameter to the loop function, which is reLOO, and what equal to true. And what that does is it takes those problematic values and it just fits them using proper leave one out cross validation, not an approximation, not the PSIS approximation. So that's how it deals with that problem, and then we get the expected log pointwise density estimates, and that's what is compared then using LOO compare, right? With LOO compare, you can see that there's a gigantic disadvantage here for the Gaussian likelihood, huge advantage for the log normal likelihood, and so there is overwhelming evidence here that Gaussian likelihood is a terrible idea. Okay. I mean, we didn't need to do a model comparison to know that because the Gaussian likelihood would anyways be predicting negative reading times. Okay. That's already nonsensical enough for me. I don't need to do any model comparison to figure out that the model is garbage. Anyway, so um, where was I? Yeah, so one important thing you can do once you've done the produce the output of the loose is you can extract the pointwise densities, the expected log pointwise densities, and you can plot them next to each other, or more precisely you can take the difference in the log pointwise densities in the two models, right? So the better model will have more positive values and the worst model will have negative values. So if you take the difference between the better model and the worst model in the pointwise densities, what you will get is, if you have positive values in the difference between the two, that means that the better model is showing a better predictive fit. So let's do that. So this is just ggplot2 code, so I won't discuss that because we're just literally extracting the difference in the ELPs on the point file as pointwise values, and then we're just plotting them. So what you'll notice is that the reading times are ranging from some short number here, like 50 milliseconds or something, all the way up to like something like, I don't know, 9,000 milliseconds, right? So 9 seconds. And so this long tail in the reading times is also going to show up in the difference in the ELPD values. And so if you zero in, on the more realistic range of reading times between 0 and 2000 milliseconds, right? So this part here, which is hard to see on the left hand side plot. On the right hand side plot, when you look here, what you'll see is a cluster of log pointwise density differences that are either above or below 0 or at 0. And so all the positive values are indicating that the log normal model is the better one here. It's making better predictions. So what we notice here in this plot is that the log normal model is producing for the largest proportion of data. So that's what the darkness of the density shows here. Okay, that the vast majority of the data is in this range here, from let's say 250 milliseconds to something like 1,000 something milliseconds, right? So in that dense region, the log normal model is easily outperforming the Gaussian likelihood. So that's where the big advantage for the log normal model comes. Here you see very sparse data in the slow values, and these sparse data points, they are being predicted better by the log normal model, log normal likelihood. The reason for that, of course, is that in the Gaussian likelihood, extremely long reading times are going to skew the condition means, because means, as I mentioned before, are highly sensitive to extreme values. If you have even one extreme value in a data set, that's going to heavily skew the mean for a particular condition, right? And there are real life examples of this being a huge problem. So there are people who have published studies in which only two extreme data points were causing a significant difference in a frequentist model. And if you damp those two extreme values, which are not even representative of reading time because they're extremely long, you don't see any significant effect. So just spurious significant effects will turn up if you ignore the fact that you're using the wrong likelihood function, in reading studies, for example. Okay, so that's basically the story with um, cross-validation, PSIS-LOO, and LOO, um, k-fold cross-validation using BRMS. Right? As you can see, it's very easy to use it without really knowing too much about cross-validation, which is actually a very big disadvantage because people often use these tools just like significance tests, like statistical significance tests. So that is kind of a misuse of this methodology, and the oversimplification that BRMS provides is on the one hand convenient, but on the other hand extremely dangerous. If you don't know what you're doing, and I've seen many papers in which people publish ELPD hat differences, and they have no idea how to interpret it or what it's even doing. Like they just don't know. They're just treating it like a proxy for a p-value. So they're doing Bayesian modeling, but you treating it like a proxy for a p-value, which of course makes zero sense. So in order to deal with that problem, what I'll do next is, in the coming sections, I will talk about how to compute the ELPD hats and the standard errors in Stan proper. The advantage of that will be that the process of generating the ELPD hats and the standard errors will become much more transparent. Okay, so you'll have a deep understanding of where these point-wise densities are coming from, right? Which definitely helps you in interpreting what's going on when you're doing k-fold cross-validation. There's some discussion about issues with cross-validation. There was a couple of years ago a big fight that broke out between the Bayes factors enthusiasts and the cross-validation enthusiasts, and they were publishing papers back and forth at each other, trying to explain why the other guy was wrong. So I won't get into that debate. I mean, Bayes factor has its own place and answers questions in a certain way. Cross validation has its own place because it's targeting held out data, right? So that's a very important machine learning method that we should be using for model comparison because it actually is more demanding in a sense. But that's just my opinion, okay? So if somebody watches this video who's a Bayes factors enthusiast, they might get mad at me for saying that. So that's just my opinion. Okay. So all right. So I'll skip over this whole thing about the complications involving cross validation, because here in this section there are the discussion, the debate between Bayes factors and cross validation is discussed, but it's really not very interesting for me, so I'll just move on. Okay, I'll get to the nitty-gritty stuff instead of talking about these philosophical issues, or maybe they are actually statistical issues, right? But they're not of interest to me. So what I'm going to do next is I'm going to talk about cross-validation in STAN, and this is where I feel that you will get much closer to the process of doing the cross-validation um, steps, and to figure out how the ELPD hats are computed and so on. The equations that I showed you at the beginning of the lecture, I mean, they are hard to understand, right? Because if you look at these equations, these guys here, it's hard to know how to translate this into code, right? If you're marginalizing out the parameters, what does that mean? I'll show you what that means, okay? And if you're calculating the expected log pointwise density of every single data point, what does that mean exactly? I mean, you can't really unpack this equation and translate it into actionable steps, in STAN code or R code or whatever. So I will show you how that works, and then you will see how this final ELPD hat and the standard error are computed. Okay, that's the next part of the lecture. In this part of the lecture, I'm going to introduce cross-validation methods in using STAN code instead of brms. And there are two different versions of cross-validation that are discussed: PSIS-LOO cross-validation and k-fold cross-validation. As I've mentioned several times, I will generally be using k-fold cross-validation, or that's what I generally use in my research. So, but it's good to know how the approximation works as well. So let's first look at PSIS-LOO cross-validation. So here, basically the only difference will be that instead of writing brms code, we'll be writing STAN code, and then in the generated quantities block in the STAN code, we are going to um, collect the log likelihoods of all the data points. Okay, after the model, the posteriors for the parameters have been um, computed by STAN, right? So the data that I look at is the old data set that we have looked at earlier. This is the pupil size data as a function of load and a function of trial and the interaction of these two. So notice here that we have centered load, we've centered the trial predictor, and the interaction term is here. So here what we have is one intercept, of course, and then three slopes, right? These are three parameters: beta 1, 2, and 3. Then there's a sigma parameter, which is the um, residual term. So we're going to define priors for the alpha and the three betas and the sigma. So this is not hierarchical because we have only one subject, I believe, in this data set, right? In this subset of the data. So what we are doing here is we are centering the predictors just like always, and then create the list object for feeding into STAN, right? So that we can fit the model. In the STAN code, there will be a generated quantities block that's going to collect the log likelihoods. So I'll show you what that looks like. So here's the STAN code. We've got the number of data points that go in here. You can see that here. Oh, where is it? Here. N is the number of rows in the data frame, right? That's N. And then the predictors, the three predictors, and that's it, right? The parameters are alpha, beta 1, beta 2, beta 3, and sigma. So there's 5 parameters, right? And then because all the parameters need priors in the model block, we define the priors just like always. So I don't need to explain that. So, and here we have the normal log PDF that specifies the model, the linear model, the multiple regression that we are doing. Main effect intercept, main effect of load, and main effect of trial, and the interaction, right? So that's all familiar, nothing new there. What's new is in the generated quantities block. So we create an array with as many cells as there are data points, and we're going to call it, we have to call it log like, because we will feed the results of this model, the object that stores the results of this, the posterior and so on, into the loop package functions. And there the loop package function will look at the object or the vector log lick, right? And it will recognize that that's the log likelihood of the data given the posteriors on the parameters, right? So we create this array, and then we run a loop that goes from 1 to capital N and stores the log likelihoods for all the pupil size data given the posteriors on these parameters. Okay. So if we are interested in finding out if there's any effect of load, what we would do is we would also fit a null model, but without this term, both in this part and in this part here in the generated quantities block, right? That would be our null model. So this is the full model that you're looking at, and then the null model, the corresponding null model would not contain the beta 1 term at all. So this will be completely gone, right? That null model is available in the bcogsap package, so you can look up the details there. And the full model is here, okay, in the bcogsap package. So we extract the two models code, and then fit the using stan. We fit the full model and the null model using the ls pupil data frame. So notice that in the we are using the same list object for the full and the null model. It's just that cload is not going to play any role. Even though it's there in the data, it's not ever going to show up. So you can look at the code to see what comes in the data block. Okay, just take a look at that yourself later on. All right, so so you fit the models. Here are the two models. But what we are, so here we've added the extension LL to stand for the fact that we have the log likelihoods in the generated quantities block, right? So if you look at, if you were to look at this data, you would also see the log likelihoods in the output, you know. Shall I just do this? Maybe not, maybe not. You can try it out yourself, okay? Just look at the results of this fitted model, and you will see the log likelihoods going from 1 to whatever capital N was it 37? I don't remember now. So anyway, so then what you do is you take the full model that we just fit, pass it through the loop packages loop function, and save the loop results. You can look at the output, and there you see again that you get the ELPD PSIS-LOO, right? That approximation. And similarly for the null model, you also get that. So now what we're interested in is the difference between this value and this value and the standard error of the difference, right? And this can be computed using the LOO compare function, just like before with brms. So the only thing that changed was this addition in the generated quantities block in the fitted in the stand code, right? This is the only thing that is new here. So we are saving the log likelihoods. and that's what Loo is using to compute the ELPD Loo here. Okay, so there's not much of a leap between using brms and the Loo package and stand code and the Loo package if you are computing PSIS-LOO. Okay, so next we turn to k-fold cross validation, or leave one group out cross validation. So the method is the same for both. So we're going to do the following. So this is where you will finally see those equations that I showed you at the beginning of the lecture. Let's go back. Right at the very outset, I had written out all these obscure equations. Now you will see these equations playing out in stand code and in R code, basically, right? I will unpack all these three equations. I will now unpack so that we will end up with the ELPD hat in the end, as well as the pointwise values for the expected log densities, right? So let's go back to our page. Right, so here we are at k-fold cross validation in stand. So the steps we're going to take are the following. We split the data into 10 folds because it's k-fold, k equal to 10. And there's a function in the Loo package that does that for you. We don't need to stratify the data because we have only one subject. So we are using k-fold split random. Okay, so just randomly holding out some data and creating 10 training sets. So what you see now is a new column here. Once I have added, so this function takes as input the data frame, the number of rows in the data frame, and it takes the k value as input, and it returns a vector called fold, which we are going to add to the data frame. So this vector now identifies which fold we are talking about, right? So these numbers will range from 1 to 10. And for example, this row is fold 2, and there will be 3 other instances of 2 in this data frame. Okay, this is fold 6, and there will be 3 other instances. So we are holding out 4 data points for these folds. There's only one exception, that in the 10th fold we have 5 held out data points, right? So this is indicating to us which data will be held out and which data will not be held out. So in fold 2, there will be 4 data points that will be held out, and the remaining data will be used for training. Here, what this says is that in fold 6, 4 data points will be held out, all the ones that are labeled 6 in the fold column, and the rest of the data will be used for training, right? So the reason I said that the 10th fold has 5 data points is that the total number of data points in the data set is 41. So we have 9 folds with 4 data points and 1 fold with 5 data points. So we end up with 41 data points that are being held out in total in the 10 folds. Okay, so what that means is that in the end, we're going to have a vector of all the held out data points, and that vector will have length 41. Right? So if you remember, let me just go back. Let me go back to this equation. It's kind of awkward to go back and forth like this, but it's worth doing. So remember that when we have k held out sets, this yk, this is a vector, will contain 41 elements in the cell. Okay, that's what I'm talking about here. Okay. So, right, so this is the layout. We have got 10 folds, and each contains either 4 data points, and the 10th for the first to ninth fold, and the 10th fold contains 5. So then what we're going to do is we're going to fit the model and extract the log pointwise predictive densities for each fold. So how do we do that? Okay, we're going to do this for the full model and the null model. Okay, so first we're going to create we're going to use this function, which I think you've never seen before. It's called stan underscore model, and take as input the full model and the null model that we extracted from the bcogsci package a few minutes ago, right? And what this does is that this stan model function, it just compiles the model. It doesn't actually estimate the parameters. Once the model is compiled, you can give any data to that model, to that compiled model, and then it will produce posteriors, right? So that's the advantage of the stan underscore model function. It compiles the model, but you can put any data later on into that model and you'll get posteriors. Okay. So what we need is a store. We need to store. Where's my? I need my iPad. So what we need to do is we're gonna have to store the log. These updates are so annoying in Apple. Just one moment. Let me just start up my QuickTime. Okay, finally I've got this going. I should have prepared the iPad in advance. But what we really need to do is for the full model, we have 41 data points that are going to be held out in total. So we're going to have a matrix that contains 41 columns, one for each data point that has been held out, and we are going to have as many rows in this matrix as there are samples. Okay, because we are fitting only one chain and we have 3000 samples. The first 1500 samples are going to be the warm up or whatever it's called, and the rest of the samples is 1500. So we're going to have 1500 samples for data point 1 and 2 and so on, and we're going to have a matrix as a result that will store each of the data points log likelihood. So what will be stored in each cell? In each cell is the log likelihood of each data point in all the samples, based on all the samples we have from the fitted model that was fit with the training data. Okay, so we're going to create an empty matrix. This will be initially filled with NAs, NAs everywhere. Okay, and we're going to do the same thing for the null model. For the null model, we're going to have 1500 by 41 matrix filled with NAs. This is initialized now. We're going to run the for loop and we're going to fill in this matrix with the log likelihoods. Okay, so let's do that. Yeah, so let's do that. So I was at the point where I had compiled the models and I've stored them as these objects: pupil stand model, pupil null stand model. I'm going to use those in my for loop now. So here's the initialization. I've created a matrix for the full model. This log PD log posterior density k fold is this matrix 1500 by 41, and initially it's going to be empty like I just said, right? So that's what it looks like, and as I said, it's going to have dimensions 1500 to 40 by 41. So do the same thing for the null model. So that's the log posterior density null k fold. Okay, same setup. So the two matrices that will be filled in incrementally as we loop through the k folds. Okay, so let's do the looping. Here's how this works. I'll go step by step through the for loop. Okay, for small k ranging from 1 to 10, okay, we're going to do the following. First, we get the training. So let's say k is equal to 1 at the beginning of this for loop. Okay, k is 1. So what will happen is that we are going to extract the training data. And what is the training data here? All the data where k is not equal to 1. Remember the fold column? We had a column called fold. This fold column will contain 4 instances of 1. So those will be removed from the picture. The remaining data is going to be now what goes into the training. So that's what's happening when k is equal to 1. Okay. So that's what this code is doing. It's extracting the training data because it's removing everything that doesn't have fold equal to 1. Okay. Then we create the list object that contains the usual information that the stand model needs. And then we are also going to extract the held out data. This time we're going to extract the 4 data points for k equal to 1 that constitute our held out data. So there'll be only 4 data points here in the first fold. Okay. So that will also be saved in the held out list object. Okay. It's just like the training setup, except we are working with a different data frame now. A data frame containing only 4 data points. Okay, for the fold, for the first fold. Okay, so there will be only 4 data points here. Yeah, right. So this is our this is the dependent measure. 4 data points, 4 data points, 4 data points, and n will be 4 because the number of rows will be 4. That's the difference between the list object for the training data and for the held out data. Okay, so then the next step, k is equal to 1 still. Okay, I'm working through the first iteration now. Then what we do is we take our compiled stand model that we extracted or we set up using stand underscore model, and then we use this sampling function which uses the precompiled model. Notice 3000 iterations, 1 chain, and the data that we set up for training for the fold equal to 1. So this gives us posterior samples, right, of the parameters after we have trained the model on the training data in the first fold. We notice that we will have 1500 samples now because the first the half of 3000 is 1500, so the first 1500 will be the warm-up and that will be abandoned, and then the rest of the samples will be used. Same setup for the null model. This is the precompiled null model. This is the training data for the first fold, and then we save the posteriors here, okay, in these two objects, fit train and fit null train. Now we're going to use that GQS function that we had introduced earlier in the course. What this function does is that it takes the pupil stand model, this precompiled model, okay, and This time it um, yeah, this extracts from the generated quantities block. Okay, generated quantities block. It extracts the log likelihoods that were defined in the underlying model that is precompiled here. You give it the precompiled model, and you extract the um, the log likelihoods for the um, for the held out data. Okay, for the held out data, so there are 4 data points. Using the draws, that means using those 1500 samples from the fitted model that was fit on the training data. So you're getting the posteriors from the fitted model, using it to compute the log likelihoods of the 4 data points that I held out, and using the precompiled stand model which contains the generated quantities block, and that gives us the log likelihoods for the held out data in the first fold. Okay. Do the same thing, exact same thing for the null model. Okay. And then what we're going to do is we're going to extract those log likelihoods for the held out data from the kth fold. K is equal to 1. So what we're doing is for k equal to 1, for fold equal to 1, we are extracting the log no, sorry, we are extracting the log likelihood from this. We're extracting the log likelihoods from this object here, which was generated from the GQS function. Okay, so this is the extraction process here, and these extracted log likelihoods for the 4 data points in the first fold, they're going to be put in. Remember, k is equal to 1 in the first iteration. They're going to be put in into the 4 columns that correspond to the first fold. So let me show this to you on the iPad. So what I'm saying is that, suppose, I'm just making this up, but in the matrix that we have that has 1500 rows, and it has 41 columns. So let's say, I'm just making this up, okay? This is just a hypothetical case. So let's say the columns 4, 8, 16, and 21 correspond to the first fold, right? So what that means is that in the data frame containing the pupil data, there's a column called fold, and so it'll be the 4th, 8th, 16th, and 21st column that contain fold equal to 1. Fold equal to 1, right? So what I'm doing is I'm isolating these columns. These columns are being isolated, right? And they are being isolated. Why? Because what I'm going to do is, remember that each of these columns represents a vector with length 1500. So what I'm going to do is I'm going to plug in the log likelihoods when k is equal to 1, we have 4 data points. What we have just done is that we extracted the log likelihoods from the GQHO object, and we've isolated, this is isolating the columns in the empty data frame that represent the 4 data points, right? These 4 data points that I just circled here, right? And remember that each of these 4 data points log likelihoods is actually a vector containing 1500 values because we have 1500 samples from the posteriors. Therefore, we are going to put in all those 1500 values for each of the data points into this empty vector. So the empty vector, empty matrix, this empty matrix, we're going to put those four vectors in the relevant columns. That's what this code is doing. That's what this piece of code is doing. Right? So what happens is that the empty, this empty matrix, this one, oh sorry, you can't see this. The empty matrix here, this matrix is going to get filled in partially with the four data points in the first iteration. So now you can imagine what's going to happen, right? As we iterate through the for loop, we're going to do this 10 times. So we'll go through folds 1 to 10. Eventually this matrix, which I've just circled, will get filled in with the log likelihoods for every single data point that was held out. Okay? That's what's going on here. Do the same thing for the null model, and that's the end of the for loop. So what you end up with in the end is a filled in matrix that contains all the log likelihoods for every single data point in the full and the null model. So we're going to use those matrices now for doing the rest of the computation. So this is just reiterating what I just said. The GQHO object contains the log likelihoods. So there'll be 41 of those, right? And because there are 1,500 samples from the posteriors, we can compute statistics, the uncertainty of each of the log likelihoods as well for the 41 data points. But we are only going to be working with this here. Okay, we are ignoring the rest of the data. Is just a statistical summary that Stan puts out, you know, to tell you what information lies inside this GQHO object. Okay, so in this particular case, I'm showing you the 10th fold. The 10th fold, remember, had 5 data points. That's why the dimensions of the extracted log likelihoods will be 1500 by 5 because there are 5 data points. Okay. All right. So this I just explained. So now all I'm showing you here is that in the 10th fold, when we are at the 10th iteration of the for loop, the columns that will be chosen are these 5 columns. Okay, that's what actually happens in this data set. Okay, so next step, now we got the filled out matrix, all the matrices for the full and null models. Then we evaluate the predictive performance of the model on all the 10 folds using ELPD. So this is again using the built-in function ELPD. What it takes as input is that 1500 times 41 matrix, and it computes the ELPD for the full model. And what you see is as an output is the ELPD hat and the standard error. Okay? Same thing for the null model. You give it the matrix that's filled out, and it gives you the ELPD hat and the standard error. So now next step will be to compare these two values, right? And that difference is will be computed with LOO compare just like before, but this time we are using not PSIS-LOO, but we are using ELPD hats. That's why you notice that when we were using PSIS-LOO, we had ELPD underscore LOO to emphasize the fact that we were doing PSIS-LOO. Here we are computing the ELPD hats because we're using k-fold. Okay, so the same function does double duty in a way here. Okay, for computing the ELPD hats. So here you can see that there's not really any strong evidence for any difference, just like what we saw with PSIS-LOO. Same conclusion, that we couldn't really distinguish between those two models, the full and null models' predictive capacity. Okay. So now the question arises, should arise in your mind, what is this obscure function ELPD doing? So what I'm going to do is I'm going to write this function out myself. just to demonstrate what it actually does. So that's this section here. So let's start by creating an artificial example, okay? So what I'm going to do is I'm going to assume that I have only 3 held out data points. These are just hypothetical numbers, not real data, of course. And let's assume that we have a ridiculously small number of samples from the posteriors, 2 samples. So it's a 2 by 3 data frame, right? 2 by 3 matrix, sorry, that contains the likelihood. So this represents, this is a toy example of the filled out matrix that I was talking about here. In the full demo, that full model fitting that I was doing, we are going to have a 1500 by 41 matrix, right? But what I'm doing right now is I'm just taking a toy example with just 2 rows and 3 columns. So 1, 2, 1, 2, 3. So these are 3 data points that I held out, and we have only 2 samples from the posteriors. Okay, so let's work with that. So what we're going to do is first we convert the log likelihoods back to the original scale. Okay, we're going to go back to densities. Why is that? So just remember at the beginning of the lecture I had said this. If you look at this code here, right, we are working with the likelihoods, but Stan provides us with log likelihoods. We're going to do the logging later. The log will be done later after the likelihoods have been summed up. Okay, so that's what's going to give us the pointwise ELPDs. So we need to get back to the original scale of density, not log density. So how do we do that? We exponentiate the data. So that's where I was. Right, I take so this matrix, I'm just going to exponentiate every element in this matrix. We get back to the likelihood instead of the log likelihood. And so these are the numbers that you get. Then you compute the pointwise ELPD hats, the equation I just showed you, okay, from the beginning of the lecture. So what we're going to do for doing this is by computing the column means. If you marginalize over the samples, that's what marginalization means. When we are talking about, let's go back, okay. If you remember this obscure equation where I say that we are marginalizing over the theta parameters, this is what I'm doing right now, okay. I have only 2 samples from the posterior. Put away my iPad. And I have only 2 samples from the posteriors, right? Therefore, what I'm going to do is to marginalize out the posteriors, I'm going to take the average of each column. Okay, so that's what the column means does. And what that gives me is instead of 2 values for each data point from the 2 samples, I get 1 average value. So this corresponds to this equation here. This equation here, this is the average, right, of the likelihoods for the samples that we have. In the toy example, I have only 2 samples. So it's divided, summed up likelihoods divided by 2. That's it. That's all this equation amounts to in terms of R code, you know. All right, so I was at this point here. I marginalize out the parameters and take the expectation, right? So that's the mean, right? Then what I get as a result is, where did it go? Sorry. Yeah. So what I end up with is 3 numbers. And then what I'll do is once I've computed the column means, now I do the log back so that I go back to log likelihood. So this is the marginalized log likelihood resulting from the calculation of the expectation here. And that logging step is going to give me the pointwise ELPDs. So what I called the ELPD underscore I earlier on in my equations. Sorry for this tedious back and forth, but here it is, right? So I take the log of the means and I get the pointwise ELPDs. The pointwise ELPD hats for every single data point, each of those 3 data points. So that's what I'm doing here. Right? So here's my pointwise ELPD. So ELPD underscore I, right, on the log scale, right? And then if I want to compute the LOO information criterion, it's just -2 times these pointwise ELPDs. So I have the LOO information criterion for every single data point as well. Okay. So, but of course, I just did this just to mimic the output of the ELPD function, but I don't really use this at all. Okay. So, and then we can compute the variance of the pointwise ELPDs. Okay, that's the variance. And then if you multiply that with the number of data points that I held out, 3 in this case, right? 3 data points were held out. We multiply the variance with the number of held out data points, take the square root. That gives us the standard error of the ELPD hat. That was discussed at the beginning of the lecture. Okay. So now we know the standard error and we know the pointwise ELPD hat. So if I want to get the ELPD, right, we're going to sum up all the pointwise ELPD hats, right? That gives me the ELPD here, the ELPD hat, right? So the sum of the pointwise ELPDs gives me the ELPD hat, and then I just computed the standard error. Okay? And the larger the value of the ELPD hat, the better the fit. Okay. So that's the same thing for the LOO information criterion and the standard error of the LOO information criterion. And the LOO information criterion is telling you how much information is being lost, so lower values are better, just to make life more confusing. Higher values for ELPD hat are better fits, lower values of LOO IC are better fits. Okay. So, but we are not going to use the LOO IC. I just wanted to mention it. Okay. So if you compare the above statistics with the output of the ELPD function, you'll see that the numbers are identical. Minus 2.1, 0.4, minus 2.1 is the ELPD hat, and 0.4 is the standard error. So we can reproduce the results. Okay. So so like just to drive the point home, I just wrote up a little function which computes my own computes the ELPD hat and the LOOs just by writing stand code. Okay. So what are we going to do? We're going to just generalize the code that I just wrote for this simple 3 data point example by giving as input a log likelihood matrix into my function here. Compute the number of columns in the matrix. That tells me how many data points I've got that were held out in the k folds. Then I exponentiate that matrix so that I get the likelihoods. Then I take the column means of the matrices. Doesn't matter how big it is, 41 data points means 41 columns. So you take the column means, log them. That gives you the pointwise ELPD hats. And then the LOO information criterion is computed just like before. And then the variance of the ELPD hats is computed just like before. And then the ELPD hats is the sum of the pointwise ELPD hats. Straightforward. And then the standard error is there too. Same thing for the ELPD. I won't repeat this because it's just kind of obvious. This is just some bookkeeping to return a result that looks similar to the ELPD has. So if I run this function, my ELPD LOO on the toy example that I showed you earlier, then I get a nice output that mimics the ELPD function, and this is, you can see that they're identical, right? So we can test this function now with the real data frame that we had, sorry, the real matrix which contained all the log PD values. This is the 1500 times 41 matrix that we filled out through that for loop. And so now I'm just rounding the result to 1 decimal point because that's what they do in the PD function. So if I look at the output of this, you'll see these numbers here, they're identical to the numbers that the LOO ELPD function produces. So now you know how this ELPD function works. Okay. Same thing for the null model. You can compare them; they're identical, right? And so the difference, the ELPD diff um, that is computed with the LOO compare function, and the standard error is pretty straightforward as well. The difference is just the difference of the two ELPDs, so that's minus 5.6. And the standard error of the difference is basically you create a vector that contains the differences between the 41 log likelihoods for the full data and the 41 log likelihoods for the null data. Do a cell-wise subtraction that gives you the difference vector, right? This difference vector d pointwise, and then you, oh sorry, there's a typo here. This should have been the variance of the d pointwise. Let me fix that right away. Oh, where is it? Sorry, standard error of the difference. So this should have been variance. Let me just rerun this code. I'm caching the model, so as a result, this thing will run relatively fast, even though many models are being fit. It's all pre-stored in caches, so everything gets done quickly. All right, so that's done. And so if we go back here, right, so what I'm doing is I'm taking the cell-wise difference between the point-wise ELPD hat values for the full and the null model, computing the variance on that, multiplying with the number of data points that were held out, square root of that gives the standard error of the difference. So that gives us the same, so here I'm doing the standard error, the calculation for the full, matrix that I had created, and so you can figure out the standard errors, right? So this is all straightforward now, I hope. Okay, so this is the cell-wise difference that I'm taking here, and then you can also plot this point-wise difference. This is very informative because if you look at the point-wise difference, this is also the plot that we saw earlier in this lecture, right? So you've got a zero line here. This on the y-axis is the point-wise difference between the two models, and these are the 41 held out data points, and you see that the difference is just fluctuating between positive and negative values. That's why we don't really see much difference between the two models. There are slightly more positive values here than here. That's why we see a minus, so a disadvantage for the null model that is by fact, like with a value of -5 or something, but the standard error is too large. There's too much variation in these differences for us to be able to say that there's one model is better than the other. Okay, so that's the whole story with k-fold cross validation. Now you can scale this up to any situation, hierarchical or not. Okay, so it's just all more of the same now. All right, so do read the chapter. There's some references in the chapter as well, and that's basically the whole story as far as we are concerned in this textbook regarding cross validation, which we'll be using in subsequent chapters.